Hi my friends, I've seen that many of you are interested in applying dynamic simulation to mechanism sketches. Here we'll discuss only planar mechanisms. As you can see, this is a planar mechanism. It is placed in the plane XY. I make visible this plane, and now we can see that once again this is a planar mechanism. Yes, the center point is important for us. To identify the position of this point, we can use UCS by placing values on axis 0, tab 0, tab 0, enter. You see, this is the position of the center point and the direction of axis, of course. You end with the finish. Okay. You can delete the UCS symbol by using the browser. Another important thing about mechanisms and assemblies with mobilities is to go to View and to activate degrees of freedom. As you can see, in this case there is 1 degree of freedom for this crank and this joint, and combination of rotation and translation for this end of the lever. We will use this all possibilities. Good. Now let's create a very simple mechanism. Sketch XY plane, line from this point, even if it is not especially necessary, with a length of 28 or any other value. Finish sketch, hide the dimension and save. We save it as part 1. Save. Okay. Next is the lever. Sketch XY line, no matter where I place it. Finish sketch, no dimension, and save as part 2. I want to be part 2. We close it because we'll use in an assembly. And now the assembly. Yes, standard millimeters IM, place. I place the part 1 right here, and then the lever. But now, because this is placed all over this space. I want to constrain its endpoint. I wait for a while to obtain the point, not the line, and I place it in the origin of the assembly, not the origin of the part. Yes? Not here, but here. Center point, apply. We lost our object, but we can place 0, tab 0, tab 0 to see that it is right in position. Escape, I don't want this here, but now we are sure that the crank is in its position. Then we place the other last object, which is the part 2. I place it somewhere here. Then I connect this point with this point, which means I apply constraint. I wait here for a while. I select the point. Then I go to the other component, wait for a while, select the point, apply, cancel. Very interesting. Now I project, or I make visible the axis X. Axis X to be visible. We don't see it because it's very small, and this is presentation color, so that if we know where it is, I don't change the color of the background. Then I place this endpoint, not line, on that line. On the line, not in any point. Okay. Now it seems that we have a mechanism which is planar. Is it or not? Let's see. Not in the plane. It is planar because the crank lever is always planar, but it is placed. Let me show you the plane XY. The plane is Y is here, and I rotate the crank. We see that it is not in the expected plane. To place this mechanism in his totality on the plane, I add constraint for this endpoint. I wait here for a while. And I select any point here. One is from crank, the other is from lever. To be placed in this plane. Okay. Now we have a planar mechanism placed in the plane XY. No doubt about this. You can rotate it, you can make anything, and it stays in the position. What we do if we have many levers and so on, we'll see this immediately. Good. I save it as assembly number 1. Okay. Now let's take a look at another aspect. I double click this and I edit the sketch of the crank. I edit it by adding in the middle a small perpendicular line. I want to be sure that it is perpendicular because everything is fluid here. Finish sketch, return, double click on the lever, double click on the sketch of the lever, and we place another short line in the middle to have a position 90 degrees. Yes, here is 90 degrees. No, now it is. Good. Return. Now we have these two small lines. One is in the plane, the other is not. Let's rotate the crank. What happens? It happens that you can rotate also this. You see, this is another position. Why happens this? Because these joints are spherical, not cylindrical. We have to respect everything, because if we apply environments, dynamic simulation, we see here spherical, spherical. Yes, we want to have cylindrical or revolution joints here. To make this, we have to apply circles at the ends of the components. Good. Save this, close it, and we create this mechanism by using circles and every other elements which you can see here. I edit each component to apply visibility of dimensions. Return, double click, sketch, dimensions, return, and double click once again. Dimension visibility, return. Okay. Now you see the dimensions. You see circles, diameter of 2 at each end of them. I don't draw them again. You can very simply create these objects. 3 objects. One is the bearing, an equilateral triangle, and a line coincident with this point. This point is the center point, as you expect, and the other. So this is the first, this is the second, this is the third. Once you have created, as you saw in my previous start of this tutorial, we can create an assembly, a new assembly, and we place that objects. This is the crank lever mechanism, and components are base with the bearing included. This is a static component, so that we place grounded at origin. Okay, now I have to hide dimensions, but only with double click here. No dimension visibility we want. Place again the CL crank somewhere, double click, sketch, dimension visibility, return. We place this and this point. Yes, constraint. First I place this line over this line, which are axis. Apply, but this is not enough. You see, cylindrical but not fixed. Constrain, wait here for a while, select point and place also in a point, no matter which one. Okay, now we can move this very well. Place lever, CL lever somewhere, change its sketch with a double click, and dimension visibility not to be present. Good. Next is to apply return and constrain. Once again, we see if we select the circle, we see a line to be placed over the other one. See? Apply. Now I can show you that the axis is maintained, but the distance not. Constrain. We wait here for a while. We select the point. Wait also for a while here. Point. And apply. We go to the other end. We select the point, the line. Okay. Now we go to the view, degrees of freedom, and we see something that you already know. See? Good. This is for us to ensure the possibility to apply dynamic simulation, to have these proofs. Now we can apply dynamic simulation, environments, dynamic simulation, and we receive the message that the mechanism is over-constrained by 1 degree. We can accept this, but we wonder why it appears, since we respected everything. Well, the problem is that the dynamic simulation is more strictly in order to respect every joint. We can change the model to have not this degree which is in excess. How can we do this? Firstly, I want to show you where is the problem. We use mechanism status, the tool mechanism status, and we see here something very interesting. Joint has 6 degrees of freedom, 3 translation and 3 rotation. The problem is with the translation on the direction Z. Oh, Z is this, yes? And we placed the end point of the lever on this line. This means that we consider both translations vertical and horizontal along this axis Y and along the axis Z. This means that we over-constrain the mechanism in perspective of the dynamic simulation. We can repair this very easily. Finish dynamic simulation. What is this last joint? Is the mate 5 between the point and the line. We can see the other half of this connection or mate, and we go to the lever and base are containing mate 5. We delete mate 5. Yes, now this is free. Good. And how to solve the problem? we can solve it very easily. As I said, we place this point, end point, not on the line but on the plane ZX. ZX, the plane of the assembly, is this. Okay. Now we come back to environments, dynamic simulation, and we don't have any other message. These are revolution and this point plane, not point line. Yes, so, or point axis. Good, very nice. Now let's see what happens if I select this tool or button. Nothing, my friends, just nothing. Why? Because there is no force in this assembly. If we place only the gravity, double click on gravity and select vector components, but let me copy this value, the gravity acceleration, copy. Now I go here and on the axis Y I place that gravity force. Okay, I click here to hide the... Oh, but this is not good. Double click here and select the other direction, which means minus. The direction of y-axis is up and we have to change it to down. Okay, click here to hide the arrow and we try again. Let me change the time, 10 seconds, not 1 second. Then once again run or play. See, the gravity without any friction is repeated all the time, all the duration, but not this is our goal. Yes. We go here and we define gravity with 0 all over, 0. Okay, there is no gravity and we see that all is statical. Good. What we do? We apply a moment here to the crank. Yes, this is the motor of the movement. So we go to the joint, double click, and this means properties of this joint. We go to degrees of freedom 1. There is only 1 degrees of freedom. In fact, rotation. We apply imposed motion because we want to impose a motion there. Enable it and select here constant value. What value? Say 100 degrees per second, but with minus, because we want to apply a movement in the direction counterclockwise. Okay, good. Click here to hide the arrows, and we start everything. You see how is the movement. I hope you understand all this. If not, ask me and I try to answer. Now you have all the data for each other mechanisms to create and apply dynamic simulation. My friends, how many components we have here? Well, we have crank placed on a bearing. Basic are this line and the bearing, which are static. Then the crank, then a lever, then a plate. This is a plate with fixed dimensions, and also another lever. There is, I forgot, this is the other bearing, which is together with the line and the first bearing. To have all the data, we go back, we double click, I call the platen here, to apply dimensions, to see dimensions, return, second, the crank, see dimensions, visibility of the dimensions, return, the lever, double click, sketch, dimension visibility, return, the plate, dimension visibility, return, and the last is the other lever, double click, visibility of the dimension. Now you see everything. Let me move the crank. Oh, return here. Let me move the crank a little, and to make these dimensions more visible, you see this is the same bearing, the line, vertical line of 135. You have all dimensions here. Take care and use them. Here is 1 millimeter diameter of the circle. You can use, and there is a point here as the end of the each line. But I consider that you can use this line to here. 1, 2, 3 lines are connected here because there is no problem. Don't complicate the situation. These are dimensions. Good. The other one is this one, which has another movement. As you can see, this is the one which has traces, interesting traces. The other don't have but circles and lines, but here we have other possibilities. We can apply a trace to this point. The color is black. You can change the color with green, for instance. Another trace is oh, I didn't apply once again with this color, apply. And now this one with the color orange. Okay, apply. Don't forget, like me. Cancel. And now we start the movement and we see that two traces. Good. What other possibilities we have? We have output grapher. To activate output grapher, now is gray because this is not in movement. If we apply movement, we stop it, we go back, and now we activate. You don't see here any gray presentation. We open this, we go to traces, we see that traces, right click, to add, to edit the trace and add the velocity and acceleration. Velocity with the color red, acceleration with the color magenta. Okay, one of the two, no problem. And then you see here that two components. We select the vector, the result, not on the axis, and also for accelerations. You see here velocity, and here is acceleration. We start with the movement, we continue it, and we have here red is velocity and magenta is acceleration. You can watch this and understand everything about this movement. For instance, you may want to have the velocity of this vertical skate. Okay, then what you have to do? Eventually you will eliminate these two traces, delete, delete the other one, go back to the origin, place another trace on each point you want on the skate. For instance, this point. This is the skate. And apply both velocity and acceleration with these colors. Okay. And now we apply velocities with the resulting vector, this, and acceleration with its resulting vector. You see, everything was memorized by the software, the dynamic simulation module, so that you can see directly the situation. But we may want to see them from the beginning. You see? Remember, this is speed or velocity with its dimensions, its values. I stop here, yes? And we have this moment of the stop. We can change it by selecting a point, double click, another point, double click, at the beginning double click, and you see the start of this. But what are the values? You see the values here. Time, double click here, no, move by hand, and you have 32.61 millimeters per second in this very moment. At the time, 0.37 seconds, third of a second about, and the acceleration is here. 112. Yes, this is 112, this point of the acceleration. And for the velocity, 32.61. This is 32.61. This is 50. You have everything at your disposal, my friends. Good. Let me show you dimensions for this assembly. Now you see also dimensions. If I move a little these components, you have a better vision. You see all the dimensions. You can create each object. This is the skate. this is the platen. I placed a lot of names here. 2 millimeters are all circles, dimension 3 millimeters for this joint, 165 for the vertical line, 117 for the distance from the center point. This is the center point, and this is a equilateral triangle. Another movement for you to see dimensions. Okay, now I think you have all the data to try for yourself any other mechanism with sketches only, without any solid object. That's all for today. Thanks for watching. Bye bye.